Hey guys, in this video, we are going to begin beam design. In this first video, we are going to learn probably more of what I would call material science or mechanics of materials. And to be honest, guys, this is a college level topic. We've done a few college level topics, and this one right here is definitely one of them. You might touch on it a little bit in physics and POE, but what we're going to be covering is things that you'll probably be seeing a lot your freshman year of engineering school if you pursue that route. So we're going to be talking about stress and strain and how that relates to the strength of a material. So let's start with, what is stress? What is strain? You probably have heard at least stress. I'm not sure how familiar you are with what strain means in a physical sense, but stress is going to be a measure of the forces acting on a member. So here's your wordier definition. I'll read it. A measure of the magnitude or value of the internal forces acting between particles of the member resulting from external forces. And you can think of stress as pressure. And what is pressure measured by? Well, it's force per unit area. Force per unit area. And here's your formula for it. Stress is force over area. Axial stress is what we'll be working with. And axial stress is just acting directly on a member in either tension or compression. And it is represented by the lowercase sigma, or the little O with the tail, a hat, I don't know. So here is just represented from this. So this is the one that you're going to be seeing. It's stress equals force over area. F is the applied force, measured in either pounds or kips. And A is the cross-sectional area, typically measured in inches squared. So it's pounds per square inch or kips per square inch, PSI or KSI. And here's just your little diagram of it. You have your member right here. And then in this case, it's almost as if you're pulling the member apart. That would be tension. So the force is the F right here. And the area is this area of the cross section right here. So you take this force, divide it by this cross-sectional area, and that'll give you the stress that's acting on this member. So let's do a real quick example. I tell you that the tensile stress on a 2-inch by 3-inch member is subject to a 45 kip load. Okay, so we know that the force applied is 45 kips, and I know that the member is a 2-inch by 3-inch rectangular piece. So we know that our formula is stress equals force over area. Force is 45 kips. You'll have to quickly calculate the area for a 2 by 3. That's easy enough. Do the division, and we have kips divided by inches times inches, KSI, or PSI. Okay, that's it for stress. Now let's go on to strain. You probably heard of like strain. You can strain your wrist or your ankle or something like that. And when you strain a body part, what's happening? You're stretching it out more than it should be, more than it can handle. You're putting pressure on it in a really weird way, and then you're causing the body part to move and hyperextend. That's exactly what strain is in a member. So strain is when the member has a change in size. So it is the change in size or shape of a material caused by an external force. You are applying a force to an object, and because of that force, you are making the object stretch. That's what strain is. Strain is a measurement of how much an object stretches from an applied load. The symbol for strain is epsilon, the little squiggly E or a sideways butt, and it is represented by delta L over L, where delta L, I think we've done delta in this class. It's like the change of. So the change of L over the original length. Let me explain this a little bit further. Here's a little diagram right here. Right here is your member. There's no forces acting on it. The length of the member is what they call L naught. not is a little zero here. So like the original, you can call it the original length. The original length of this member is right here. Then what happens? We apply a force. Imagine this big burly dude grabbing both sides of this rod and stretching it apart. And what's going to happen to the member? It's going to elongate. It's going to elongate this delta L right here. This is how much more the member has been stretched. So the strain is going to be a measure of how much it's elongated. So you would do this distance right here divided by the original length, change of L over L. And the units for this is actually interesting because it's unitless. So if I say, let's just throw in some numbers. Say this was 7 inches and this was 8 inches. The strain would be the difference, which is 1, divided by 7. So it's 1 inch divided by 7 inches, which would be inches over inches, which actually cancels. So strain is actually a ratio. It's technically unitless, but we prefer to say inch over inch. So this would elongate 1 inch per 7 inches, or whatever 1 over 7 is. I don't remember that one. 0.14 or something. So 0.14 inch for every inch of length. Let's go to another example. Calculate the strain if a 16-foot long structural member elongates 1.5 inches when subject to a tensile load of 67. Okay, so I know that we're applying a force, but do we really need the force in this one? Let's look at the equation again. It's change of L over L. Actually, I don't even need the tensile load. I can tell you what the strain is just by saying, okay, change of L is what? What is the change in L? How much is this piece elongating? Answer it. How much is this piece elongating? Good. It's like we're in episode Dora the Explorer. 1.5 inches. Okay? And then we're going to divide that by the original length. What is the original length? Wrong. It's not 16 feet, because if we say 16 feet, we have inches over feet. So you have to convert 16 feet to inches. So I'm going to do 1.5 inches divided by 16 feet converted to inches. So my strain is 0.0078 inches per inch. So what that means is for every 1 inch of member that I have, it is going to elongate 0.0078. I can now tell you how many inches this will elongate no matter what length the object is. If I tell you that it's a 10-foot long structural member, you can now tell me exactly how long it'll elongate. It'll be this times the length of it. Okay, so that was stress before. This was strain. And we're going to move on. So what is the relationship between stress and strain? Well, I think you should know, just from living on this planet for 15 plus years, that the amount a material stresses or strains is related to how much you pull it or how much stress it sees. Think of a rubber band. Now, I want you to imagine a rubber band in your hand. And then when you pull the rubber band, you're applying a stress. And what happens to the rubber band when you pull it? Well, it expands. That's strain. And the more stress you apply, the more strain you apply. And once you stop applying the stress, what happens to the rubber band when you stop pulling on it? Well, it goes back to its original size. Strain goes to 0. And then if you pull too hard, it does not return to the original size. It gets deformed, it might even break. That physics is exactly the same for a steel beam. It's just that with steel beams, we're talking a lot more stress than what your puny arms can actually apply. So, another way we could illustrate this is by blowing up a balloon. Let me fix that little typo right here. I spent a lot of time on this lesson. This was by far the longest one. Ha, look, 67 slides. Have fun with that one. Okay, So there's a little YouTube video that I'm going to show you, and spoiler alert, the balloon does not burst. So we'll watch this real quick. And I don't think that in this free version of the software I'm using to make this video that you're able to use computer audio. So I'll play through it and kind of give you the commentating. I do encourage you to watch it on your own as well. So we are going to be looking at blowing up a balloon, and then we're going to look at the stress and the strain and the relationship between them. So again, stress is the force over a cross-sectional area, and strain is the measure of how much it elongates as compared to the original size. So you have your balloon right here. Here's your original balloon size. As you add air or you increase the pressure or stress, what's going to happen to the balloon? It's going to increase in size. We then like to put the stress versus strain on a graph, where on the y-axis, you're going to see the stress, and on the x-axis is going to be your strain. And then as we increase the stress, we're going to see what happens to the strain. So we start with our balloon, and we're going to start filling it up. And as we fill it up, we're adding a lot of pressure, right? Like it started with a pressure of 0, and then we're adding a lot of pressure. But did the strain really increase that much? Not really. So we see a pretty steep start where the stress is increasing a lot, but the strain's not moving that much. And then eventually, when you get to a certain point, you're going to have a lot of balloon increase in size without adding that much more air. So look, there's steady increasing in size, not that much more air, not that much more pressure being added. So it's going to be a nice slow. And then what happens is once the balloon reaches its full capacity, it's not going to increase in size too much, but you're going to keep adding more air, you're going to keep adding more pressure, and eventually the balloon will burst. So that right there gives you a little quick idea of stress versus strain. That gives us this graph right here. This is a measure of the stress versus the strain. So materials all have different stress versus strain graphs. Every single material has a different stress and strain graph. Every single one. Most metals have a little bit of a more direct or linear stress and strain relationship than the balloon. The balloon had a little bit of a linear in the beginning, but not that much. Like metals will be a little bit more like this. So here's another video I want to show you, but I think we're gonna run out of time, so I'm gonna end the first video here, and the next one will take off where this left off.